A traditional software scan evaluates a package and outputs a reassuring green "zero threats found." But the moment that same approved package executes, it immediately opens a red, reverse shell initiated network connection. The code passed the test, yet the system is compromised. This disconnect is actively playing out in the ecosystem of AI coding agents, like Claude Code and OpenAI Codex. These agents acquire new capabilities by loading skills, small third-party packages that function as an extensibility layer. Because a skill is essentially just a bundle of markdown instructions and scripts, it executes with the agent's full system access. It inherits your local file read and write capabilities, your stored credentials, and direct access to your terminal. Most public marketplaces allow developers to upload these skills with minimal vetting. This creates a massive, open supply chain attack surface. The scale of the exposure is severe. When security firm Bitdefender analyzed one major public marketplace, they found that 17% of the available skills contained hidden malicious code. That is nearly 1 in every 6 downloads. In a single documented campaign known as Claw Havoc, attackers distributed over 800 distinct malicious payloads disguised as legitimate tools, directly targeting users who install agent skills. The security model for AI agents is actively failing because it relies on traditional software defense mechanisms. Attempting to secure a highly dynamic runtime environment with static, pre-execution checks creates a massive vulnerability. Currently, the primary line of defense across these skill marketplaces is static security scanning. These systems analyze the code at rest, looking for known malicious byte sequences using pattern matching and regular expressions. Research from the Hong Kong University of Science and Technology reveals that when attackers apply specific evasion techniques, these static scanners suffer a bypass rate of over 90%. This is a systemic collapse. The researchers tested the evasive skills against 8 major security scanners, and every single one failed to detect the cloaked threats. Attackers achieve complete stealth through simple mechanical transformations, bypassing the need for sophisticated cryptography. They rewrite the code so it becomes entirely invisible to static analysis, while remaining completely lethal at the exact moment of execution. To secure the AI ecosystem, defenders must move beyond pre-execution, scan-at-rest methodology. The trust boundary must shift entirely to runtime behavioral monitoring. The university research maps exactly how this is done through a tool called SkillCloak. The first evasion method is lightweight character obfuscation. Static pattern matching scanners have a rigid reliance on predetermined byte sequences. If they do not observe the exact bytes of a known dangerous command, they approve the code. This diagram shows a Python snippet executing the dangerous eval function. The attacker simply replaces the standard Latin letter E with a visually identical Cyrillic E. The regex scanner fails to flag the code because the byte sequence has changed. The pattern doesn't match. But to the Python interpreter compiling it seconds later, the characters are functionally identical and the code executes perfectly. The researchers also exploit a secondary mechanism, the new line splitting operator. By fragmenting a continuous string, like a destructive system call, across multiple lines of code, the attacker breaks the scanner's string matching logic. The complete signature is never visible in a single pass. At execution time, Python's native line continuation seamlessly pieces the fragments back together, reconstructing the dangerous command directly in memory. Static analysis is inherently flawed here because it evaluates the rigid syntax of the code on the page. It cannot predict the semantic intent of the interpreter executing it. The second evasion technique, self-extracting packing, weaponizes a deliberate performance optimization made by the security vendors themselves. To process uploads quickly and reduce false positives, every static scanner is programmed to deliberately skip over metadata directories, specifically the hidden.git version control folder. In this directory tree of a skill package, the attacker isolates the malicious payload, encodes it as a block of raw base64 text, and hides it inside the excluded .git directory, disguised as a configuration file. Back in the main directory, which does get scanned, the attacker leaves a tiny, benign decoder script. This decoder easily passes static analysis. To the scanner, it appears as a standard, harmless file read operation, simply instructing the system to check a config file. At runtime, the approved decoder reaches into the unchecked .get directory, It extracts the base64 block, unpacks it into executable code, and pushes the malicious instructions into live memory. The attack succeeds because the static artifact reviewed by the scanner literally does not contain the malicious system that ultimately executes. The payload builds itself after the scan is over. To stop these exploits, the researchers proposed an architectural defense called Skill Detonate, moving the security boundary into an isolated sandbox environment. The core operational difference is that Skill Detonate ignores what the code looks like. It exclusively monitors what the code actually does at the operating system level. The central defensive concept driving this system is called taint propagation. This data flowchart illustrates how taint propagation tracks sensitive data by its path rather than its content. When a block of data representing an ATI key is extracted from a secure .env file, it instantly turns solid red. The system marks any data pulled from a high-security source as permanently tainted. Here, the red data block moves into a processing node to be encoded. Even if the attacker scrambles the stolen data to hide it, the monitoring system maintains tracking. The block exits the encoder visually transformed, but the core red taint color remains. The attacker could even wrap the data in AES encryption. It becomes a complex geometric shape, totally illegible to a pattern matcher, but that red taint color persists. The system triggers a detection the exact moment that heavily transformed red block attempts to leave the local environment through an outbound network socket. It forces a hard stop and generates a warning indicator. The exact nature of the obfuscation along the path is completely irrelevant to the sandbox monitor. If sensitive data moves towards an exit, it gets blocked. This dynamic execution visibility also immediately neutralizes the self-extracting packing exploit hidden in the .get folder. Because the sandbox actually executes the decoder script, the system watches it pull the base64 text and convert it. The hidden payload becomes visible to the monitor the exact second it is unpacked in memory. You can mathematically disguise what malware looks like on a hard drive, but you cannot hide what it actually does to an operating system when it runs. The empirical results validate this approach. The researchers tested over 1,600 real-world malicious skills against both defense models to measure the difference. In this bar graph comparison, we established the baseline performance of the industry-leading Cisco scanner. Against uncloaked, obvious malware, it successfully detects 99% of the threats. Once the SkillCloak evasion techniques are applied, the Cisco scanner's detection rate violently drops to just 10%. We contrast that failure with the Skill Detonate behavioral monitor, running those exact same obfuscated skills. Its detection rate rises to and holds steady at 97%. Crucially, Skill Detonate achieved this detection rate while generating only a 2% false positive rate. These results confirm a systemic failure inherent to the static analysis approach itself. There is a primary limitation to dynamic sandbox analysis: the speed of execution. Static scanners complete their checks in fractions of a second. Behavioral detonation requires several minutes per skill to properly observe the operations. However, this latency is paid once by the marketplace infrastructure before a skill is ever published. It is a necessary upfront operational cost to close a 90% security gap. In an ecosystem where AI agents actively pull external data, dynamically construct commands, and operate with user privileges, trust can never be established pre-execution. The artifact reviewed is not the system that executes, and security must live exclusively at runtime.